All right, y'all, so the point of this video is to go through a criteria C and kind of talk through some of the important things that you might need to pay attention to as we're doing that, okay? Now, in this specific one, we're looking at a variety of different organic compounds. These are all hydrocarbons. And as we look at these, we can see that we're comparing molar mass and boiling point, all right? Now, yeah, it's in alphabetical order right now, but I mean, that doesn't really help us understand what's going on here, right? As we look at this, we can see that the molar masses are changing. They're different for each of these. That means some of them are bigger. Heptane's obviously the biggest, and methane is the smallest. But then it also gives me some information about boiling point. Now, what could I get from this? Well, I mean, maybe boiling point depends on molar mass. Maybe the bigger something is, the higher or lower the boiling point is. But that's really hard to see the way that this information is prepared right now. So what I would say in this first question suggests a more useful way of organizing, presenting the table in the table. Well, I would go straight to put it in order, right? Start with the lowest molar mass and work our way up to the largest one. Now, why would I do that? Well, if I can see how molar mass is increasing, then possibly I will be able to see how boiling point is changing. Is boiling point increasing, or is it decreasing, or is it just random? Maybe they don't have anything to do with each other at all. But right now I can't tell. So that's going to be my first step, is I'm going to put it in order. So that's what we're going to do on the next page. All right, here we go. All right, so this is the table I ended up with. You'll notice that I did the molar mass in increasing order. I started with smallest one, 16, right? So that was the methane there. And then I went all the way up to the largest one, okay? And then I corresponded that to their boiling points. And I noticed that when I do this, the boiling point starts at the lowest, and then it gets all the way up to the highest. So it certainly does show that as the molar mass increases, the boiling point increases. Now, it's a little difficult to tell what type of relationship it is. Maybe it's linear. I do see that there are some kind of common differences between these as I look, but I also know that there's some bigger gaps down here at the bottom. So I'm not 100% sure whether this is actually linear or not. I'm going to go ahead and put it into my graph, and maybe once I put it into my graph, I'll have a better idea, right? That's what's going to happen on the next page, is I'm actually going to take this data and put it into the graph. Notice that one of the things that I did here was I included a title. If you go back to the first page, you'll notice that there was no title there. That actually made it really difficult for us to know what we were supposed to be getting out of the table at all. You know, when we looked at it, we could eventually kind of figure out I'm comparing these two numbers, but at the get-go, it would be really helpful to have a title there that says, hey, you know what, this is what you're supposed to be looking at, the molar mass versus the boiling point. And so now I can see that, and I've got it. That gives me a little more indication that being in order would be helpful. All right, so now let's go ahead and go on to the graph, okay? All right, so I've copied my table over here. Now, as I'm creating my graph, I want to do a couple of things. The independent variable, the thing that is most easily changed, that's the molar mass. That's kind of what we're controlling by choosing, you know, methane or ethane or propane, right, is I'm choosing the molar mass. So that's going to go down on the x-axis. So I need to make sure to label that. So I'm going to put molar mass down here. Now, from there, I'm not just going to put these numbers down, right? I'm going to go ahead and start at 0. So this is going to be 0 right here. And then from there, I need to increase until I get to 100. So I'm going to go by maybe tens. So 10, 20, 30, right? I think if I do this, it's pretty clear that I'm going to be able to fit up to my 100. A little extra space is okay, because I know later it's actually going to ask me to extrapolate. And so I might need a little bit of space later. Don't do something weird like go by 3 squares or something. That makes it really hard to estimate later, right? This is going to make it really easy for me to be able to figure out where in this range it's going to be, all right? So now that's the molar mass. Now I'm going to put the boiling point on. Now the boiling point is going to go on my y-axis, okay? Now one of the things, I should have put this on my x-axis. This is grams per mole. On the y-axis, boiling point is going to be degrees Celsius. And we'll notice that we have negatives and positives, which is fine. That just means that when I go up my axis, the 0 can't just be down at the bottom. I've got to put the 0 somewhere else. So I'm going to make sure that I can at least fit that negative 162 on there. So I'm going to go, this right here is going to be negative 160. So the 162 is going to be just below that. And so then I'm going to go, this one will be negative 150. And then I'm going to go by tens. So 40, 30, 20, 10. So this right here is negative 100. 90, 80, 70, 60, 50. So negative 50, 40, 30, 20, 10, 0. So this is my 0. So this is actually my x-axis right here. All right, like that. And then I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I managed to fit all the way up to my 100 there. All right. So now I can go ahead and put the points in. So I'm not going to make you watch me put the points in. I think going through the reasoning of how to put these things on the axes was probably helpful, but you don't need to watch me put the points on. So I'm going to pause it. Ta-da! All right, there go all my points. Now from this point, it is usually valuable to connect the dots, but we don't connect the dots by making a zigzag that connects the dots. Really, we want to try to model what's happening here. Now, there's a couple of different things you could say. You could say at the end it looks fairly linear, right? And if you wanted to draw a straight line for the points kind of up on the end, that's fine. But the points at the beginning here are actually, they're pretty clearly, there's a curve to those, right? And so I would at least for the first few points put in some kind of curve that looks like it's going like this, right? And then honestly, I would probably just continue with the curve going on that way, something like that. All right, and that's what my graph would look like, because I think that a curve fits it a little bit better than a linear graph does. Okay, now again, if you wanted to curve the first part and then make the second part linear, that's fine, right? But it's a little difficult to reason why nature would do that. Nature tends to follow pretty simple, straightforward patterns, and so if one curve fits it, then I'm just going to do the one curve. All right. Now, from there it says, what can you conclude about the relationship? To me, it looks like it is nonlinear, but as molar mass increases, the boiling point also increases. Okay, now sometimes you can give an actual mathematical relationship. This one, because of the curve, I don't know, maybe it's a square root, maybe it's some type of exponential or logarithm or something like that. But I think it's okay here just to say it looks like it's non-linear, and it's pretty clear that as molar mass increases, the boiling point increases. That's it, right? If it was a straight line, you should mention it's linear or it's proportional if it goes through the origin, right? That type of thing. Remember that proportional, you only use this word, proportional, if it is linear and through the origin. Okay, that it goes through 0, 0. If it doesn't go through 0, 0, then it's not proportional. It could be linear, but it would not be proportional. So remember that as you go through future assessments and relationships and physics and chemistry classes. All right? Okay, let's go on to the next page. So here it asks us to use the graph to extrapolate the boiling point for a compound with the molar mass 142 grams per mole. So I'm actually going to copy over my graph from the previous page. Bloop. All right, so the first one wants us to extrapolate. Extrapolate means to find something outside of the tested range, right? So my tested range only goes up to a molar mass of 100. They want us to predict for a molar mass of 142. So I need to go out to 100, 110, 120, 130, 142. So that's about here. Now, if I go up to 142, and I create my line I need to find where I think that my curve is going to meet with that line. And so if I continue my red curve from this point, I'm going to say it looks something like that. And so I'm going to predict this point right here. Now what that means is that I actually need to extend my boiling point graphs. So 110, 120, 130, 140, 150. I'm doing my best to kind of keep those evenly spaced. But eventually, right, it looks like it's going to go right through my question there, and that's all right. Okay, so right somewhere around there. So 110, 20, 30, 40, this is 150, and then 160 would be right there. So somewhere between 150, 160. So I'd guess it looks to me like it's a little bit less. So I'm going to go about 154 degrees Celsius. All right. Now yours may be slightly different. That's fine. But basically you're going to create this line. This line is at 142 grams per mole. And then you're going to find where does that intersect your line, depending on if your line is a curve or a straight line or whatever. And you're going to figure out where that actually then meets up over here with your boiling point. Okay? That's it. That's it. And if you did your line slightly different, you may get a slightly different answer. That's fine. Okay, now for part C, it says, using your graph, determine the molar mass at which a substance is likely to no longer be a gas at SATP. So SATP, remember, is standard ambient temperature and pressure. So that standard ambient temperature and pressure is 25 degrees. So if I go to 25 here, so I'm going to go right here, and I'm going to go along 25 as best I can. So that's right here. So anything that has a boiling point below that, right? So all of these, they're going to boil at a temperature lower than 25. That means 25 is too high for them. So these will all be a gas. Anything above that, these are all a liquid. Because in order for them to become a gas, they need a higher temperature. They have a higher boiling point. So therefore, what I'm going to do is I'm just going to go from this 25, and I'm going to go straight down to the axis here. And so for me, it looks like between about 65 and 70. So I'm going to say 67.5 grams per mole. And anything bigger than that is going to be a liquid at SATP. Anything below that number is going to be a gas, because 25 is hot enough that it's already over the boiling point, and so it's going to boil away. All right, it's going to be a gas. That's it. That's it. So that's how we use our graph. That's how we use our data in order to analyze the data and come up with some other predictions and some other answers. All right, hopefully that was helpful. We'll talk to you later. See you next time.